Now we're going to talk about the stereochemistry of monosaccharides. Then we'll talk about another classification system that we use that uses stereochemistry. Before we move into the monosaccharides, let's talk briefly about stereochemistry. And so we'll need to look at structure to see what happens. We have two different structures here, and recall that if there is something that is different on one of the carbons, we need to have 4 different attachments. We call that an asymmetric carbon. So here we see this one has 4 attachments and this one has 4 attachments. They both have the same groups attached, but one of them we consider left-handed and the other one would be considered right-handed. Now let's apply that to our straight chain monosaccharide. Let's do a 5-carbon one, and we're going to make this an aldose. So an aldopentose. And the challenge I have for you is to find out how many asymmetric carbons there are. So go ahead and pause the video while you count them. So we'll start at the top with carbon number 1. We see that it is an aldehyde. 2 of the bonds go to oxygen, so this cannot be an asymmetric carbon. And on the next one, we see that there's a carbon. It has a hydrogen and an OH. Those are the easy two. Coming up above it is an aldehyde carbon. Going down is a bunch of alcohol carbons. So that is 4 different groups attached to one carbon. Since they are all different and there are 4 of them, that is an asymmetric carbon. All right, let's go down to the next one. And here we're going to see that there's an H and an OH. And then going up from that carbon, we're going to see at the end there's an aldehyde, and at the other end there's another hydrogen or just an alcohol. So carbon number 3 is also an asymmetric carbon. Now let's look at carbon number 4. For number 4, we see an H and an OH. We see a long chain going up, ending with an aldehyde, and a short chain going down, ending with an alcohol. Those two are different, so we have 4 different groups, and we have an asymmetric carbon. And finally, let's look at carbon number 5. On carbon number 5, you'll see that we have a hydrogen and an oxygen, and then we have another hydrogen. Notice that I said another hydrogen. What that tells us is those two are the same atom, so this is not an asymmetric carbon. The way that we're going to label this is we're going to put a little star next to each of the carbons that are asymmetric. So here we have our overall structure, and we see we have not asymmetric, and then we have 3 asymmetric ones, and then a not asymmetric one at the bottom. Now that we know how to identify the asymmetric carbons, we can continue with the stereoisomers of monosaccharides. So what we're going to do with this is we're going to find out how many different stereoisomers are present in a specific compound. So we're going to look at the number of stereoisomers, and it is going to be related to the number of asymmetric carbons that you found on the previous set. The number of stereoisomers is equal to 2 to the power of n, where n is the number of asymmetric carbons. So for example, in an aldohexose, how many asymmetric carbons are present? Pause the video while you figure that out. Hopefully you saw that there were 4 asymmetric carbons. The top one is not because there are 2 bonds to oxygen. The second one is because we have an H and OH, an aldehyde going up and not an aldehyde going down. The third one is an asymmetric carbon. The fourth one is an asymmetric carbon. The fifth one is an asymmetric carbon, and the sixth one is not asymmetric because the 2 hydrogens are the same. So we end up with a total of 4 asymmetric carbons. Now we're going to use that 2 to the nth power to find out how many total stereoisomers there are. In this case, we just found that n is equal to 4, so this is going to be 2 to the power of 4, which is the same as 2 times 2 times 2 times 2, a total of 4 of those, and that is 2 times 2 is 4, times 2 is 8, times 2 is 16. So 2 to the power of 4 is 16. That means there are 16 stereoisomers. It ends up that some of these match, and they are exactly the opposite of each other. When they're exactly the opposite of each other, we call them pairs of optical isomers. So one is all the OHs are on the left, and the other one has all the OHs on the right. And those are optical isomer pairs. So how many pairs are there? Every time we say there's a pair of them, there's going to be half as many. So we had 16, we go down to 8. This is similar to the way that we talk about socks. If I say I have 20 socks, How many pairs of socks do I have? Well, I have 10 pair. And here we have all 16 aldohexoses. What I'd like to do first is count how many pairs there are. So notice that there are 8 pairs. So these two are matched, 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 and these two are matched. And notice that they have the same name. So they're both called allose. These two are both called altrose. These two are both forms of glucose. We're going to talk next about how we identify one from the other. There's going to be a slight change in their name as we do this. While I have provided you the names here, you will not need to know how to name any of these. But you should know how to do the calculation. How many stereoisomers are there? Now I'm going to have you try it. What we're going to do is we're going to find first the number of asymmetric carbons, n. Then we're going to find the number of stereoisomers, that's that 2 to the power of n. And then we're going to find out how many pairs there are. So we're going to do that for each of these in the model shown. I'm going to do the first two, then I'll pause it and you can do the rest of them. Okay, let's start with the aldotriose. Here we see that there are 3 carbons. The top is an aldehyde. And then we see that there is only one asymmetric carbon. That's this one right here. That bottom one is not asymmetric because it has 2 hydrogens attached to the same carbon. And then that means that there are 2 to the power of 1 stereoisomers. 2 to the power of 1 is 2. And so we have 2 stereoisomers. How many pairs is that? We just cut that in half. We end up with 1 pair. Let's look at the ketotriose. Now the ketotriose is a little bit different. It's going to give you a different answer and it will be unusual. You won't see this all the time. We can see that carbon number 1 on the top has 2 hydrogens that are the same, so it is not asymmetric. Carbon number 2 with a ketone has a C double bond O, which means there's 2 bonds to oxygen, so it is not asymmetric. And of course the bottom one, which has 2 hydrogens on it, is also not asymmetric. And that means that in the ketotriose there are 0 asymmetric carbons. That means the number of stereoisomers is 2 to the power of 0. Everything to the power of 0 is 1, not 0, but 1. So there is one type of molecule that has this structure, and it is this ketotriose. And then we want to know how many pairs are there, and that would be half a pair. I would not ask that on an exam, just letting you know that's how you would do it. Now you can go ahead and try the rest of them. Pause the video while you do them, and then turn it back on, and I'll go over them. Let's start with the aldotetrose. We see that there are 2 asymmetric carbons. The top one is not asymmetric because it has a C double bond O. The bottom one is not asymmetric because it has 2 hydrogens attached to the same carbon. So n is equal to 2. To find the total number of stereoisomers of an aldotetrose, we will have 2 to the power of 2 in this case, which is 4. There are 4 stereoisomers of aldotetrose. How many pairs is that? 4 divided by 2 is 2, so there are 2 pairs of aldotetroses. Now let's look at the ketotetrose. Here we see the top one is not asymmetric because there are 2 hydrogens on it. The second one is not asymmetric because there are 2 bonds to oxygen. And we see the next one is asymmetric because there are 4 different things attached. And then the last one is not asymmetric because there are 2 hydrogens on that carbon. So our n is equal to 1. 2 to the power of 1 is 2. So we have 2 stereoisomers of the ketotetrose. And that means there is 1 pair of stereoisomers. Now let's try the aldopentose. For the aldopentose, we're going to mark the asymmetric carbons. The top one is not because it has 2 bonds to oxygen. The next one is. The next one is asymmetric, and the next one is asymmetric. All of them have an H and an OH. And going up from the end, we're going to see that there's a aldehyde. And going down from that carbon, we'll see that there's a hydrogen on the other end. These are different from each other, and so we know this is asymmetric. Each of those are asymmetric. The bottom one is not asymmetric because it has 2 hydrogens attached to it. So altogether we have 3 asymmetric carbons, and that means our number of stereoisomers is 2 to the power of 3. 2 to the power of 3 is 2 times 2 times 2, which is 8. So there are 8 stereoisomers of aldopentose. How many pairs is that? That's 8 divided by 2, 4 pair. Let's go on to the ketopentose, and we're going to see that the top one is not asymmetric because there are 2 hydrogens. The second one is not asymmetric because there are 2 bonds to oxygen. The next one is asymmetric because there's a ketone above it, but not below. The fourth one is asymmetric because we have a ketone when we go up eventually, and down below we have no ketones, so there's a difference there. It is asymmetric. And the last one is not asymmetric because there are 2 hydrogens attached to that carbon, so it's not asymmetric. So our number n, the number of asymmetric carbons, is only 2. The number of stereoisomers is 2 to the power of 2, which is 4. The number of pairs is 4 divided by 2, which is 2. Okay, let's look at the aldohexose. For the aldohexose, we're going to find the number of asymmetric carbons. The first one is not asymmetric because it's got 2 bonds to oxygen. The second one is asymmetric. The third one is asymmetric. The fourth one is asymmetric. And the fifth one is asymmetric. The sixth one is not asymmetric because it has 2 hydrogens bonded to it. So they are the same. So here we have n is equal to 4. The number of stereoisomers is 2 to the power of 4, which is 2 times 2 times 2 times 2, which is 16. And we have 16 divided by 2, 8 pairs of isomers. And finally, we're going to look at our ketohexose, and we're going to find out how many asymmetric carbons there are. The first one is not asymmetric because there are 2 hydrogens attached. The second one is not asymmetric because there's a C double bond O. The next one is asymmetric. The next one is asymmetric. The next one is asymmetric. And the bottom one is not asymmetric. That's because there are 2 hydrogens attached to that carbon. So in this case, n is equal to 3 because we have 3 asymmetric carbons. The number of stereoisomers is 2 to the power of 3, which is 2 times 2 times 2, which is 8. So there are 8 possible stereoisomers. How many pairs are there? It's going to be 8 divided by 2, which gives us 4. Hopefully while you were doing this, you found an easy pattern to find out how many asymmetric carbons there are. To see that pattern, let's look at the aldoses first. So first, we're going to see that the aldose itself, the aldehyde part, is never asymmetric because it has 2 bonds to oxygen. So let's go ahead and cut that one off. And then we see that the one below it is always asymmetric. And we see that the bottom one is never asymmetric because it has 2 hydrogens attached to the same carbon. So we can see that overall, it's never the top one, it's never the bottom one, but every one in between is an asymmetric carbon. And now let's look at the ketoses. So when we look at the ketone, we know that the ketone is not asymmetric because it has a C double bond O, 2 bonds to the same oxygen. Now let's look above it and notice that that carbon is never asymmetric because it has 2 hydrogens on it. And if we look below, we see that normally it will have anything below it will have asymmetric carbons, and then the very bottom one is not asymmetric because it has 2 hydrogens again. And so we should see the pattern that anything below the C double bond O but above the bottom one has asymmetric carbons. So I like to summarize it this way. All of the carbons between the C double bond O and the bottom are all asymmetric carbons. So I'll model it quickly for each of these. So recall, it's everything between the carbonyl group and the bottom. So here we have the carbonyl, here's the bottom, there's 1 asymmetric carbon. For this one, we see here's the carbonyl, here's the bottom, there's nothing there, so there are 0 asymmetric carbons. For the aldotetrose, we see here's the carbonyl, here's the bottom, we see that there are 2 carbons in between, they are both asymmetric, n is equal to 2. And for our ketotetrose, we see that here's our carbonyl, here's our bottom, there's only 1 carbon in between. There is n will be equal to 1. And for our aldopentose, here's our carbonyl, here's the bottom, there are 3 carbons in between, That means N is equal to 3. And for our ketopentose, here's our carbonyl, here's the bottom. There's only 2 carbons in between. N is equal to 2. For our aldohexose, here's our carbonyl, here's our bottom. In between we have 4 carbons. All of them are asymmetric. N is equal to 4. And finally for our ketohexose, here's our carbonyl, here's our bottom. In between we have 3 carbons. N is equal to 3 for the ketohexose. Now let's focus on why I kept asking about how many pairs of these isomers there are. The reason is because they are matched sets and they are mirror images of each other. And it ends up that in nature, only half of them are commonly made. The other half are not natural, although they can be man-made, they're not naturally made. That means we only have to name half of them because we could say one is this type and the other type is that type, and then we just have the common name, let's say glucose or something like that. So how we're going to name them is dependent upon how their structure looks like glyceraldehyde. Now glyceraldehyde was chosen as the base because it is the first one that has an asymmetric carbon, but it only has one asymmetric carbon. So everything is compared to that. Glyceraldehyde has 2 stereoisomers. We call one D and one L. It has to do with how they rotated light, although you don't need to know about that. But what we could focus on is how when we drew the structure, the OH was on the left or the right-hand side. And you'll need to be able to identify the D and the L sugars. So I'm going to show you the way that I remember it. And that is that the OH that we see here at the bottom is on the left-hand side, so that will be an L glyceraldehyde. The D is on the right side. D and R doesn't go together as well, but L on the left side makes a lot of sense. So remember, L means to the left, that OH is to the left. Now what's unusual is that everything will be compared to that, and when we're doing the comparison, we always compare the second to the bottom one. So it is the last of the asymmetric carbons that we're going to always compare to decide, is this a D sugar or an L sugar? So for example, here we have glucose, and we see that the first one has the OH on the right side. That makes that a D sugar, and the second one has it on the left side, so that is an L glucose. So this will be called D glucose and L glucose. Only D glucose occurs naturally. L glucose is man-made, but it has no biological activity. It doesn't taste sweet like the glucose does. It doesn't get digested, and so it is not biologically active. So let's go back to our page where we had all of the stereoisomer calculations and decide if what we're seeing are D or L sugars. We'll start with our aldotriose, which is actually our glyceraldehyde that we had from the start. And we're going to see that this is the OH we're looking at. It is on the right-hand side, and so we see that this is a D glyceraldehyde. And the next one does not have any asymmetric carbon, so we don't have to worry about that one. It is not D or L, it's just a ketotriose. Then we have the next one, which we look at aldotetrose, and we look at which of those OHs. So we have 3 different OHs. Notice that we do not count the bottom one because it is not asymmetric. And we are going to focus on the second to the bottom, and that one's on the right side, so it is a D aldotetrose. Let's look at the ketotetrose. We ignore the top one because it's not asymmetric one. We ignore the bottom one because it's not asymmetric. We go one up from the bottom. We see it's on the right-hand side. This one is also a D sugar. Looking at the aldopentose, we look at the bottom one. We do not count it because it has 2 hydrogens on it, so it's not asymmetric. So we go up one, and we see that that one has the OH on the right side, so it is a D sugar. Next, we have a ketopentose. Again, the bottom one does not count because it's not asymmetric, and the one above it has it on the right side, so it is another D sugar. Our aldohexose, we don't count the bottom one. We go up one. We see it's on the right side. This one is also a D sugar. And finally, our ketohexose. And guess what? We have another D sugar. We don't count the bottom one. We look at the one just above it. We find it's another D sugar. And I did draw all of the D sugars. Again, that's because the D sugars are naturally occurring, so I tend to draw those D sugars. Now if we go back to the page where we had the aldohexoses, we'll start to see some L sugars also. Let's look at the aldohexoses and decide if they are D or L that are shown here. So we'll start with allose, and we'll look at the very first one of the allose, and we'll look for the one just above the bottom one, and that one is on the right side, so that is a D allose. The second one has the same exact structure except that OH is on the left side. In fact, all the OHs are on the left side. We only worry about the one that is the second to the bottom, and we see it's on the left-hand side, so that is an L sugar. Now we'll look at altrose. We see the first one, the OH is to the right, so that is a D sugar. The second one, that OH, second to the last one, is on the left, and that is an L sugar. And it ends up that all of these are following that pattern. First the D, then the L. First the D, then the L, and you see that pattern throughout this set. There are three hexoses that are very important in the body and in chemistry and biochemistry. And so I'm going to have you recognize these three by structure. The first one is glucose, and glucose is an aldohexose. Galactose is also an aldohexose, and fructose is a ketohexose. But the first one is D-glucose. And again, I'm doing all the D sugars because those are the naturally occurring ones. So right away, we know that it's going to have an aldo at the top. It's going to have a CH2OH at the bottom, and it's going to have a D sugar on the bottom, second to the bottom one. So now all we have to do is kind of figure out where the other OHs go. And the hard one is this number 3, the OH is on the left side, whereas all of the other ones are on the right side. When we look at galactose, we see that there are 2 of them to the left side, and that is number 3 and 4 are on the left side. And that's our galactose. All the others are on the right side. And then we look at the last one, fructose, and we see that again, the number 3 sugar is to the left, but this is a ketose. Now, glucose and fructose are very, very similar to each other. It's just a matter of whether one's an aldehyde or a ketone. The rest of the structure will match. So again, these are the 3 monosaccharides that you should be able to recognize in this class and in your bio courses, because they do use a lot of glucose throughout those biology courses. What is the function and occurrence of glucose, galactose, and fructose? That means where do we find it and what does it do? Well, glucose is the major carbohydrate in our blood. It is the one that we test for when we check for diabetes. How much glucose is it? They're always checking the blood glucose level. It is found in nature in both honey and fruits, found freely. And glucose is the major monosaccharide used to produce all of the polysaccharides that we study in this class. Although some of them use other ones, the vast majority of polysaccharides use glucose. And that is because the ring form of glucose is the most stable of all of the aldohexoses. Next we can see galactose. Now galactose is unusual. It is not found normally by itself. It is generally found bonded to glucose in the disaccharide lactose, or we find it commonly on the surface coating of cells in the glycolipids. Remember, that was the sugar, the monosaccharide found in the glycolipids. The most common one is galactose. And our last one of the 3 major hexoses is fructose. Fructose is found in equal amounts with glucose in honey. It is very common in honey and in fruits. It is also commonly found in the disaccharide known as sucrose, which is table sugar. Our body can readily convert fructose into glucose, which is done in the liver. While this does cause some extra work for the liver if you have a large amount of fructose, the biggest problem is if you have a high, excessive amount of fructose over a long period of time, you may start to see something called fatty liver disease, where more fat is stored in the liver because of all the extra calories from the fructose.